we talk about this Hilbert transformation. And I stopped here, and I indicate that as Hilbert is one of the greatest mathematicians, and he has such a handy transformation that convert any real value x into a y and x and y form an analytical pair. Once we form an analytical pair, we can have a and a amplitude as a function of time, theta as a function of time. And the result is something like this. Suppose we have a data like given by this blue line, yeah? And if we pick up a point like here, and we go through Hilbert transformation, what will we get? We will then immediately indicate that the amplitude, the local amplitude is this much, and the local period is that much. Yeah? So, however, we don't use the whole sine or cosine function. We only use this one point. For that particular point, the amplitude and the phase is given. Now, if we change my point to here, then the local amplitude will be that much, and the period will be this. Again, we don't use the whole curve. If we use the whole curve, it becomes Fourier. And if we use one point, that's Hilbert. So therefore, my amplitude changed from point to point, from time to time, and my phase is also changed. This is great. And if we can have this, then we will be able to describe the amplitude and the frequency change as function of time. Why don't we not using it? The fact is that this does not work. And the reason it does work is, for example, if I give you a function like this is the data from 1962 to 2003. Yeah, this is a length of day. The length of day indicates that the rotating speed of the Earth is not constant. It's vary from day to day, from season to season, from year to year. If we measure the rotating speed of the day relative to a fixed star, for example, rather than look at our watch, if we use a star as a reference, then the rotating speed, we can record the rotating speed. This is the record of 40 years of rotating speed. If I give this data a Hilbert transformation, what do we got? We got a jumble like this. Yeah. Now this, I can suggest to you, whenever you see any data or any pattern which looks totally random, that means it contains no information. Yeah. Why is this? This is because we'll come back later to tell you why. So this axis is the real value. This axis is imaginary value. Yeah. So this is the phase plan. You get this. However, in this we can also define the phase function. This phase function is defined like so, and the phase function will oscillate and suddenly the jump, and then oscillate, suddenly jump. Each of this jump, if you check, each of this jump is 2 pi. Yeah, it's not a random jump. It's definitive change, a multiply of 2 pi. For example, here it will be 4 pi. What does that mean? That means it missed one cycle, missed one wave. Yeah. If you expand any area, like I pick up any area to expand, you will find that within that area, it again has structure. If you expand this, it again has structure. This embedded regular structure hierarchy inspire people to say that this phase function is fractal. Yeah. In fact, back in the 1980s, Dr. Michael Berry is a professor at Bristol. He's a fellow of Royal Society. he wrote many papers talk about the phase function of a random number, random like white noise. Then he established a very interesting theory. That is, if we have a wide band, unlimited band, none of our data is on the unlimited band, white, but a limited bandwidth, because our data has a finite length. Yeah. If you have infinite length data, then your bandwidth will be unlimited. For unlimited bandwidth, this function, the phase function of that random noise, will become a Weierstrass function. What is Weierstrass function? Weierstrass function is a pathological function that is everywhere continuous but nowhere differentiable. Yeah. So if you look at this, fortunately, our number is not Weierstrass function. We can still differentiate it because our data is finite. Okay. If we just force ourselves, so I will take a differentiation because this is phase function, time derivative of phase function should be frequency. I can define instantaneous frequency by taking differentiation of the phase function. What I got? I get this value. This value here is 0. So our number is both positive and negative, almost symmetric. The reason it's almost symmetric is that every time the wave going up, you get positive. Every time the wave coming down, it's negative. Yeah. So we have an instantaneous frequency, both positive and negative. This is totally useless. This instantaneous frequency is nonsense. It does not make any sense. Does not give us any information. This has been done by Hahn, H-A-H-N. He wrote a book on Hilbert transformation and its application for data analysis. And that book proposed this kind of solution. It's totally useless. The book is not very old. It's 1995. Yeah. Why this is not working? I will give you a more concrete example, simpler example that you can see why. I plot a sine wave given in the blue curve, and I move the sine wave up a little bit. This move up is only 1/2 of its amplitude. And then I move it up 1.5 amplitude to this red. So they are all sine waves. Now we know Hilbert transformation of sine gives you cosine. So if we do Hilbert transformation to these 3 sine waves, what do we got? We got 3 circles. The reason is that Hilbert transformation does not see constants. So the real number is 0 centered, 0.5 centered, 1.5 centered, give you red. The imaginary number is only sine wave, only cosine. So it's 3 circles at a different center. Yeah. And for this 3 sine, if we want to define its phase function, what do we got? To define phase function on the blue circle, it's very easy because you just trace around the blue circle with constant speed. You will have a monotonic increasing phase. But when we do this to the off-centered circle in the green, this circle is eccentric. Yeah. So when you try to plot that, then it's not uniform anymore. And that is not the most serious problem. The most serious problem is coming to the red. When you come to red, your center is still here. When you count the phase angle, you start at any point, you rotate. The angle increase to this point, and the curve come back, so it decrease. So as a result, your phase function becomes monotonically increase, uniformly increase the blue, which is the centered circle, the eccentric circle give you wavy lines along that. And the red one is you go up and down. You will never go beyond 2 pi, plus minus 1/2 pi. Yeah. So as a result, you get the 3-phase function. If we take derivative of this 3-phase function, we have a constant frequency for the circle that is right at the origin, with the center at the origin. For the green one, because it's it's wavy. Sometimes it's slower, sometimes faster, slower, faster, slow, faster, and it gives you this. And for this value, we have problem. The problem is we have increase and then a negative slope, and a positive slope, negative slope, and that's why we get this negative value. Yeah. Now, even if we adopt the mathematician's point of view, negative frequency, so what? Yeah, let's use negative frequency. But the fact that for a circle, just because where the circle is, you will have different values. I only give you 3 examples. I moved half of the diameter and half of the radius and 1.5 of the radius. I get these 3 values. I can theoretically move the circle anywhere continuously. So the value of the frequency will cover everywhere. And that means if I want any value, I can move my circle and get that value for you. And that's not science, and that's no good. Yeah. Because of this, then we decide the only one frequency that actually represents the original sine function is this one, because we know the function, and this one gives you the correct answer. So based on this simple observation, we deduce the following conclusion. That is, if you want Hilbert transformation to give you the correct local frequency, the wave has to be symmetric with 0 and right at with 0 lines on 0 line. In other words, this line, this wave has to be sit right at your coordinate with no offset. No asymmetry. Like this wave is asymmetric with respect to the x-axis. So the only wave that will give you meaningful answer are the ones that is right on the x-axis and symmetric with x-axis. Yeah. And why we get this kind of jumble is because each time you take a derivative, take a transformation, this is a real value. So the real value goes up and down, and that means the real value goes up and down, up and down. And the imaginary value also goes up and down. Each time you go forward, the imaginary value will also be changing. And when it comes back, it gives you a loop. Yeah. So whenever you have double hump, you will have a loop. That means the double hump means a wave way beyond this. So when the wave trough is above 0, this minimum point will be beyond 0 point. So you will have a loop. It may not have a perfect circle. It will have a loop everywhere. Yeah. So based on this observation, we decide that any data, if you want to use Hilbert transformation, a necessary condition, not sufficient. The necessary condition is to move all the way to 0 line. Okay. So how can we do that? If we take any data, will this satisfy the condition, necessary condition? The answer is no, because 0 is here. Look at this wave. This wave is our class C. That means the trough is above 0. Yeah, look at this wave. The peak is below 0. Yeah, look at this wave. It's asymmetric with the 0 line. So none of the wave actually satisfy the necessary condition of using Hilbert transformation. So because of that, the Hilbert transformation has never been seriously used. There are few people use Hilbert transformation, and they actually use it correctly. Are those people like Professor Langevin-Higgins and Ken Melville? This is the one that I know. They try to use Hilbert transformation to study ocean waves. And the way they did it is to take the data and pass the data through a bandpass filter. They select a very narrow band. If you select only one value, you have a sine wave. You select a finite band, you have a modulation of that. So they get a modulated wave. That modulated wave is still zero-centered. Yeah. So for this kind of wave, it already failed the necessary condition. We cannot use Hilbert transformation. How can we use it? The only way that we can use it is to move the wave down to the horizontal line, the x-axis. And that's where the EMD comes in. The EMD is a method to move all the way down to the 0 line. Yeah, down to the x-axis. And the way that we did it is to identify all the local extremas. Yeah. And then you divide the local extrema into two groups. One group is maximum, the other group is minimum. And you connect all the maximum with one continuous line. In this case, we use a cubic spline. And you connect minimum with another cubic spline. So this upper and the lower cubic spline encompass most of the data. There are a few points, maybe not within this envelope, that very few points. So you can see the upper envelope and lower envelope is totally independent. They have no relationship to each other. They're not symmetric. They go anywhere. However, if we define another line, this is red line. The red line is defined by the mean of maximum minimum. Yeah. Now, notice, when I say mean, I average maximum minimum. In statistic sense, average of maximum minimum is not mean, it's median. Yeah. Mean has to invoke the curve itself. I did not. I just used maximum minimum. I used the median. It turns out the median is, again, the correct guess. We will come back to that later. Once you get the maximum minimum average, you get this red line. Because I have everywhere I have envelope, so this red line is also continuous. Yeah. Now, once I have that, this red line serves a good purpose. That is, it divides the maximum and minimum in two sides. All the maximums on one side, all the minimums on the other side. And this line is a mean or a median, a random value. But the random value, I did not invoke the data itself. I used the envelope. So this way, it solves one very troublesome problem, is to how to determine the mean of a non-stationary data, non-stationary time series. Average, mean means integral over a period, over a finite duration, and divided by the duration, that's the mean. Yeah. Now, therefore, the mean value very much depends upon the duration that you choose. Yeah. For stationary process, it's no problem. The stationary process everywhere is the same. But for non-stationary process, the duration becomes important. Yeah. So in here, I did not invoke duration. I only use upper and lower envelope to define this mean. And this mean is the local mean. Yeah. The local mean is a oxymoron. That means it shouldn't make sense. What do you mean local mean? Mean has to involve a period. But now you say local, that means you involve no period. This is exactly what we got. We have a local mean. This value is local mean for here. You change another value, it's local mean for other place. And this gives me a very useful quantity. If instead of 0 here, if I change my horizontal axis to the red line, then all the wave will be near symmetric, or if everything's work right, it's be perfect symmetric, because it's up and down, it's the same, right? So how to do that? To make this our coordinate, it's very easy. You just take theta minus that red line. Take the difference. Once you take the difference, voila, you see that I move this wave down here, and I move this wave up there. I move all the wave to the horizontal line, to my x-axis. Yeah, and all the wave moved up, and up and down according to the location. And this, by construction, all the maximum should be positive, all the minimum should be negative. Yeah, if you check, indeed, all the maximum are positive, all the minimum are negative. You check all the way until you come to here, then you have a anomaly. This point originally is not an extrema, but by construction, because this curve goes through so close to that inflection point, it becomes an extrema. Yeah, this kind of inflection point actually represent a hidden scale, and this scale is there, but it does not present itself as a maximum minimum. But you can see there's some sort of wave there. Yeah. So in this way, we actually identified it as a wave. Now, because this still does not satisfy, this particular part does not satisfy the Hilbert necessary condition, we can do it another time. So we will plot the upper and lower boundary, lower envelope again. Now, when you plot this, you find now this upper and lower envelope becomes much more symmetric. Yeah. Until you come to here, it is not symmetric. And whenever it does not satisfy the condition, it's not symmetric. So we can do this repeatedly. Each time we do, we will make this more symmetric, and as this becomes more and more symmetric, this becomes more and more flat. Yeah. The goal is to make this a flat line, but that goal will never achieve. Now, when we achieve that, then it drains all the information out, and that has been proved by Wang Gang. Yeah, theoretically, that it's not going to work through this definition. Yeah. So here we come to the first dilemma that we have. We want to have it symmetric, but we don't want it to perfect symmetric, because perfect symmetric will not work. So what is the optimum time for us to stop? What is the optimum point to stop? That becomes a critical question for us. That is the stoppage criteria. Yeah. So we can keep on doing this until the algorithm is x minus the first mean, get the first data. The first data come over, move it over, then we can have the second mean, and we keep on doing that until we get a case time. Yeah, the case time, the original proposal is the case time has a stoppage criteria. The stoppage criteria is the k minus 1's time minus the case time. If the difference compared to the value that we got is small, then we stop. This is an a priori criteria you set over there. Yeah. So once it achieves that, we stop. And when you stop, you will have the stop criteria is very critical. We will talk about that in the class. Yeah. When we stop, we finally get this value. This function is the one that we finally call the C1. The C1, after you satisfy the criteria, we call this an intrinsic mode function, empirical mode decomposition, intrinsic mode function. This function has a very interesting property. That is, all the maximum are positive, all the minimum are negative. And the number of extrema and the zero crossing has to be equal, at least differ by 1. So you have one maximum, you have a zero crossing, you get a minimum. One minimum, you get zero crossing, you get a maximum. Yeah. And this function, this kind of function, has been studied by S.O. Rice, who is a very famous statistician working with Bell Lab. And at that time, what he found is that any function, any Gaussian process, if the number of maximum and minimum, the number of extrema equals to the number of zero crossing, the signal is narrow band. Yeah. Now we look at this function, we know it's not narrow band. We have a very big wave and a very tiny wave altogether. So bandwidth has to be pretty wide. Yeah. So without any proper name, I designate this function as an intrinsic mode function. Yeah. The intrinsic mode function is that any function having the same number of zero crossing and extrema, and also have the symmetric envelope defined by local maximum minimum. Yeah. This function satisfies the necessary condition, not sufficient, necessary condition for AT, EI, theta T. We'll come back to this later, when it fails. Okay? This is the necessary condition we satisfy. So we can write it as A, T, EI, theta T. Once you have X minus this first component you get out, you have a residual. What does the residual looks like? The residual looks like this. Yeah. You look at this residual. What this residual means, what this residual means physically to you. This residual means physically to me is that it goes through each wave, bisect each wave. Even this small kink, it bisected. So it is indeed a smooth mean going through all the wave. And if you take the difference between this and that, you get a symmetric wave, up and down. Yeah. So this wave is compared to the original first trial. It looks like this. The first time is here. Then through each iteration, we push this, eventually we push this to the red one. Yeah. And when you push this to the red one, so you bisect this wave, you bisect that wave. You bisect all the perceivable fluctuations. Yeah. Eventually you get that. So the residual, this residual, you can see, this residual contains lots of information because whatever you got away from the residual are the high frequency fluctuation. This residual, all the large wave, the big wave, longer frequency wave, longer period wave, it's still here, still fluctuating. Yeah. So this residual has information. We treat this residual as data. We go another step. You get R2. And you keep on doing that until to the Rn. Rn then becomes monotonically increasing or decreasing, or monotonic function. At least it cannot have two extrema. If you have two extrema, means it has a cycle in there. Then I can take it out. Yeah. So after this becomes a monotonic function or even constant or zeros, most of the case, if the value, if the data has a zero mean. So then you sum all this up, you add this up, you see that the R1 and R1 cancel, R2 and R2 cancel, all this residual cancel. And finally, what you add is X minus summation Cj to the n equal to only one that you have not canceled out, this Cn. That's the final residual. Yeah. So this way, you treat the data by peeling off each cycle, each possible cycle. How do you define cycle? The cycle is defined with two extremas. Yeah, two extrema of the same sign, two maxima. One maximum, one minimum doesn't count. Okay, so so this one is it's going to be monotonic. At most, has one extrema. It can have a general hump, but no minimum. So this function then can then be expressed by a sum of Cj. Each Cj is an intrinsic mode function. Yeah. So we expand, in this case, we expand X out in terms of intrinsic mode function. Therefore, the intrinsic mode function becomes our expansion, the basis of our expansion. Because this Cj is derived from the data, it's based on the data, so it's totally adaptive to the data. If you change one point, this changed, the whole set changed. Yeah. So in this way, we can expand, like the data, we can decompose into this component, this component, this component, and eventually come down to almost zero mean. Yeah. So all this function can be written as A E I theta t. Then if I make a Fourier transformation of I omega minus omega t, I get this omega. Then the question I want to ask is, what is the maximum contribution of this value to omega value? By stationary phase approximation, you take a derivative of that phase, set that equal to 0. So time derivative of phase equal to omega. This is the classical wave definition of frequency definition of time derivative of phase function is your frequency. So time derivative of phase as our frequency is satisfied with stationary phase approximation. Stationary phase is one asymptotic expansion methods that that is very well established. And because the theta t is function of time, so time derivative of the theta t is also function of time, so omega is a function of time. This is our instantaneous frequency. Yeah. Compare with the frequency definition we had before, is 1 over t. This is very, very different. 1 over t is a mean. Mean over the whole wave. I have to have a whole wave before I can have a period. And this one period over t is my frequency. That's a very, very crude definition. Just like this, what's the velocity? Velocity is distance divided by time. Sure, velocity. But this velocity is a mean velocity. How long a distance to travel? Over what time? So you have a beginning and end point. So this is a mean. Yeah, you're driving from A to B. In between, you can be faster, you can be slower. Yeah. So velocity should be time derivative of position. Yeah. By the same token, 1 over period is the mean frequency of one wave. Yeah. The actually velocity frequency should be time derivative of the phase. This is not new. Everybody knows that. And most of people know that. I shouldn't say everybody. Most people know that. Because this is given in many, many textbooks. But the problem is, up until this time, no one can find this theta for a generalized data. If I give you generalized data, the best people can do is to go through Stephanie Hines method, and that will give you nonsensical instantaneous frequency. Only by going through the steps that I just described, you will get a meaningful instantaneous frequency. Now, this is what they call the HHT. The HHT versus FFT is very different. This is, FFT is defined by Fourier. Fourier's work is great mathematical point. This is, I didn't say that, Lord Kelvin said that. Lord Kelvin is a great scientist. He really thinks Fourier is great. Fourier indeed is very valuable mathematical tool. I believe it's arguably the most popular mathematical tool that we ever use, almost anywhere. You can use it to solve differential equation. You can use it to do spectral analysis. But when Mr. Fourier first invented this in 1807 on a heat conducting problem, a warm body to a cold body put together, how the heat transfer from warm to cold. Yeah. So he used Fourier series to expand that out. And for that work, he was given the grand prize by the Paris Institute. Yeah. After he got the prize, he wanted to publish the paper. The paper was rejected by Lagrange. Yeah. Lagrange said that they still leave something to be desired on the score of generality and even rigor. This is not rigorous. Yeah. Their main objection is that Fourier correctly claimed that Fourier transformation can be applied to a discontinuous function. If the function has a jump, then Fourier said, fine, no problem. If you do Fourier expansion, at the jump point, it converts to midpoint. Very reasonable suggestion. Lagrange said that, well, you have to prove to me, how can you use continuous function like sine, cosine to simulate a discontinuous function? If you cannot do that, I don't believe it. I mean, you tell me that you use sine, cosine, each one is continuous, and you can get it to jump. Show it to me. Fourier cannot prove that. Not Fourier cannot prove that. The next 2 generations, people cannot prove that. The final proof was in 1935 by Poincaré. Poincaré introduced measure theory. He said that, all right, this is my Fourier transformation. This is your function. Let's see what's the difference between the two. Yeah, the difference between the two, at the jump point, I exclude all the jump point. Okay, all the jump point, I take all the jump point out. I cut it off. You can have infinite many jump points, but it has to be countable. You cannot have non-countable, it's denumerable. You have to be able to count. If it's infinite many, but the countable jumps, the measure is 0. So add up all this little thing, add up to 0. Therefore, the difference is, if I exclude the jump point, and with the jump point it's the same, therefore it converges. Yeah, it's proven that way. That's way beyond what the Fourier can do. It has to wait until Lebesgue integral and all that comes into play. Yeah. So Fourier didn't get his paper published, but he waited until 1815 or 1813. Lagrange died, and he was elected to the Academy. And then he waited another 5 years. He got appointed to the permanent secretary. Yeah. And by permanent secretary, he was able to make all the decisions, and he decided to publish his thesis without changing a word. Yeah. And that's what we see. Of course, if you look at the history, the history is a little bit more favorable to Fourier is he did not make the decision himself. So after Lagrange died, everybody think, well, this looks good enough. So everybody agreed to publish, not just Fourier himself. However, being elected to the academy and being the permanent secretary helps. If he didn't do this, perhaps people would just forget about this paper. Yeah. Anyway, Fourier's work is great. How great it is that you give any function, I can expand it out to A, J, E, I, omega, J, T. A constant, omega constant. That's Fourier's work. This is groundbreaking. This is really important. But what is our transformation? Our transformation compared to Fourier, it's very different and also very similar. Yeah. The similar in the way it's also amplitude and phase. The difference is amplitude is function of time, frequency is function of time. So recently at the meeting last month, Professor Tom Ho from Caltech is the director of computational and applied math. He designated this as a generalized Fourier expression, or instantaneous Fourier mode. Yeah. So in this way, you change the amplitude to a variable. That's a big change. You change the frequency to a variable. That's again another change, big step. To give you examples of why this thing is so dramatic, if I put in any function that phase, the frequency keep changing. This is what in double E we call the chirp. Yeah. And chirp frequency is everywhere. Chirp frequency signals everywhere. And when I talk, I speak in chirp. Because if I don't change my frequency, I will make just only one single monotonic sound. And that would not carry any information. The reason that my speech carry information is because my frequency keep changing. My amplitude also change. I stop, I start, I pause. Yeah. So how to represent this? If you give this to Fourier, what the Fourier will do, say, all right, fine, this is time. I plot the time. So now I do Fourier transformation. Fourier transformation say amplitude is constant. This is amplitude. Once I decide amplitude is constant, frequency is also constant. This is frequency. So Fourier expansion, each expansion is a straight line along this line. Yeah. So Fourier transformation, if you expand it out in time, frequency, energy space, actually look like this. Because along time axis, there's no information. If there's no information, why should I plot it? So most people don't plot Fourier this way. Because you plot this way, make yourself look foolish. So what Fourier did is to project this down to just the time, energy, frequency space, which is just this curve. Yeah. And that curve is the Fourier spectrum. Now you ask Fourier, so explain that to me. Fourier said, well, whatever your signal is, frequency here is maximum frequency, and then you have many other frequencies. How many others? 1,024 points, you get 512, right? 512 other waves of different frequency, different amplitude. Then you ask him, so where's that wave? You come here, you find this. Nowhere you can find that wave. Yeah, I cannot find the wave. Fourier said, well, look harder. You still cannot find it. So, all right, add it all up. Miraculously, when you add up all 512 sine wave, it comes back to this. Yeah. This is what I say, that when you process data, you get mathematically meaningful components like this. But physically, it doesn't make sense. It does not give you any information. It does not reflect the fact that my frequency is changing as a function of time. No matter how hard you do, there's no information along time. Yeah. So by the late 70s, early 80s wavelet people comes around and says, aha, look, this is time, this is frequency. I can find the frequency change as function of time. So that is what we call the time frequency analysis. So full wavelet solved that. Of course, at that time, spectrogram also is available. Spectrogram can also see some of that. We'll come back to that. If you use Hilbert, it's just one line. No leakage, no end effects in the transformation and all that. So this is the comparison. A data from Fourier all the way to here. We have a clean picture of time, frequency, energy. Yeah. I did say speech is chirp. This is when I say hello. Yeah. This is hello. Yeah. Digitized. And if I use all different representation, these two, top two, it's not Fourier, but it's a Fourier-based spectrogram. Okay. The first one is finite time. I use 1024 points for each window. In that case, I will have the frequency constant, just like what I showed before, during that duration. And the frequency was very clearly defined. I have a main frequency here and other frequency. All of this are harmonics of of my voice. Yeah, you can see the harmonics everywhere, all the way up. Why we need harmonics? Because my speech, my voice is not sine wave. To cover that sine wave, you use the main one, and the main one doesn't work, use the double, and so on and so forth. Now, if you ask, you say, well, this time is too broad, so it is smeared. I want to find out exactly what the frequency occurs at exact what time. You shrink the time down from 1024 to 64. The time is more local, the frequency blows up. So the frequency cannot be defined very well. So this time and the frequency cannot be both defined precisely, is what we call the uncertainty principle. Yeah. So using integral transformation, you suffer this consequence of uncertainty principle. I cannot define both time frequency. So here comes the wavelet. The wavelet is, oh, I can do that. Yeah. But wavelet suffers the same uncertainty principle limitation because wavelet is integral. Yeah. Wavelet wavelet give you much better presentation than that. Looks much better. But the fact here you can see that wavelet suffers. Where it suffers, the frequency resolution is very poor. Here you get one big blob. When you look at this, I have many different frequencies. Yeah. So what wavelet give you, compare wavelet to spectrogram, you can say this. Spectrogram has uncertainty principle. Spectrogram has different resolution for different frequency. For long frequency, my resolution is not very good. But for higher frequency, my resolution is very good because you get finite window. For high frequency, you get hundreds of waves. For low frequency, you only get a couple waves. So this frequency is very poor. That frequency is very good. But in between all this, every spectrogram has the same finite window, so the resolution is not uniform. But the resolution not uniform. Some of the resolution is very good, some is very poor, some is in between. Even the in between one is better than that. Okay, but what this is better than that is that wavelet people say, my resolution is not very good, but my resolution is uniform. Because the window keep expanding. Each window contains the same number of waves. So it has the same resolution here as here as here. So the wavelet gives you a uniform resolution picture, and this gives you a non-uniform resolution picture. Some are better than other places. This is everywhere the same. So that's the advantage. The disadvantage is this uniform resolution is uniformly poor. Yeah, you look at this, compare this to there. This resolution is much poorer than that. But they get this low frequency. This cannot get it. Yeah, so you gain some, you lose some, but they're all limited by the integral transformation. Yeah. Now, when we come down to Hilbert transformation, we have a totally different situation. We don't have the uniform resolution or not uniform resolution. Resolution is all uniform. We don't have window because the frequency is defined by differentiation rather than integration. Yeah. Time derivative of the phase. And because of that, we have this low frequency clearly defined. We have other frequencies like this, also clearly defined. Not only that, it has all these fluctuations. Yeah. Now, don't be fooled by the fluctuation. The fluctuation is very, very useful information. And this fluctuation later will show, this fluctuation represents nonlinear oscillation. Yeah. Because when I talk, my voice is not sine wave. My voice is distorted sine wave. And each one distorted their voice differently. That's why my voice is not as pleasing as the actors. Yeah, movie actors, singers, their voice is so pleasing because it's full of harmonics, quote unquote, full of harmonics. And in my term, it's very, very nonlinear. So that make it sound so good. So you look at this means that when you give one signal, we can have all different kind of representation. Yeah. Fourier, you can get this and you can get somewhere in between or beyond. You can get longer and you get even shorter. Yeah. This is still the standard way of treating speech. Yeah. Now you can tell me what is the advantage or disadvantage of that. Yeah. Now we have these two available. Okay, so Fourier is incapable of represent temporal variation. Fourier spectrum has another interesting thing. I meant to add the view graph, but I forgot. Once you get a spectrum, power spectrum, Fourier cannot go back because the phase information is lost. Power, power spectrum. It's not Fourier transformation. Fourier transformation has the inverse transformation, but power spectrum does not convert back. So because of that, if you play with the phase, you will have the same spectrum, but totally different time signal. Okay. The most interesting picture that I like to show was the one that I saw in June at the HHT Third International Meeting. Professor Mandich showed a very nice example. I meant to include that. I will bring that next time. What he showed was that two pictures. One picture of a little girl, the other picture of a automobile tire. Yeah. And then when you do a Fourier transformation and you swap, you keep the magnitude, but swap the phase. So you use the tire phase for the girl's phase for the tire. Then what happens is that the tire becomes the girl becomes the tire. Yeah. So the phase determines everything, not amplitude. But unfortunately, our attention is still attracted by the amplitude. Yeah. So this is the thing that I want you to be really aware of. What we got. Remind me of getting that. Getting that. That's the so-called surrogate picture. For a simpler case, I can explain to you, is that delta function. What is the delta function? The spectrum of delta function? It's white, right? Delta function is white spectrum. What is white noise? It's also white. So if I have a white spectrum, you ask me, so what is signal? It can be either white noise or delta function. How can you tell? You cannot. What's the difference? The difference is in the phase. White noise, the phase is uniformly distributed. Delta function, the phase is locked. All the phase has to be at one point. So, therefore, the phase is all important. But do we get the phase information when we do Fourier spectrum? No. When we do Fourier transformation, we do get the phase information. But the phase information is lost. But when you come down to phase information, that creates another problem, physical problem, not mathematical problem, physical problem. For example, I did say that a delta function is white. Okay. Suppose in this room, I turn everything off, and I play with the switch. I switch it on and off. Once, I get one flash. It's a delta function. What's the spectrum? White. How can you tell this white spectrum is delta function? So I'll give you all the phase. The phase is phase locked at that particular point. But at the very beginning of the time, the phase is already determined. The phase does not wait until the flash time. So therefore, before I turn on the switch, you have to determine the phase. So you have to have information in order to reconstruct the signal long before the event even happened. That's not physical. So the Fourier, the integral transformations, all kinds of physical problem, not mathematical problem. Mathematician doesn't care, okay? But for us, we do. All right. So noise and delta function. I have a movie, but somehow this movie doesn't work. I will not will not talk about that. Here now we have this. Can we turn this light off? Yeah, it'll be better. Then my face will be dark, right? Sorry. All right. My face will be dark. Let's leave it on. I'd rather show my face than the face. This is the data. This is our old friend. Again, this is length of day data. And if we do the decomposition, what do we got? We get the 12 components. Yeah. This data consists of 14,000 data points. 40 years. Each year is 365 days. Yes, nearly 14,000. So for 14,000 data, I only get 12 components. But if I expand in Fourier, I get 7,000 components. Yeah. So this representation is what now a ongoing mathematical pursuit. That's sparse representation. You want to represent something with as few components as possible. Yeah. The lesser the components, the more information it contains. For 12 components, I represent the whole thing, whole phenomenon. Means each component has to be very rich in information. If you do Fourier, 7,000. To this, 12. Let's forget about the first two. We will come back later. This is the first component that actually has some big value here. This is 0.5, this is 0.05 now. This 0.5 value, if you expand it out, this has sine wave, has sinusoidal type of oscillation like that. But just look at this component. This component as a gradual modulation, up, down, up, and down. This gradual modulation, the period of that is roughly 20 years, more precise, 19 and a half. Yeah. This is what they call the Metonic cycle. It's discovered by the Greek astronomer Meton. This represents the phase of sun and moon come back together. The moon and the sun were not in phase all the time. It will never be in phase exactly all the time, precisely. But every 19 and a half years, they come in pretty close. It's about 2 hours difference. They will be in phase. And that is precisely the lunar calendar and the solar calendar come back every 19 years. Yeah. And this actually is half monthly time if you look at all this little wave in that. And not only that, you look at these little bumps. Each little bumps means spring time and fall time. And spring and fall time are different from summer and winter time. They're bigger. Springtime and fall time are bigger. So this is the bigger bump. And when you come down to this point, the spring and fall time somehow disintegrated. Yeah. This is not because of global warming. It's because we get more data and we have noise. Yeah. This noise showed up here, for example. These are the noise of the storms. The data we collect here, how come there's no storm? The data collected here is very crude. Each time we determine a rotating speed of day, we have to average over a couple of days, several days, because the data is hard to get. You observe the star, you don't see it, okay? You wait, whatever. But over here, we have satellite, we have GPS. We can determine the rotating speed of the Earth, hour by hour, if not minutes by minutes. Yeah. So this data is very, very clear, very dense. Now, when you get very dense data, you can define the rotating speed of Earth better, but it also noise comes in. What's the noise? The storms. The big storms will actually influence the rotating speed of the Earth. Yeah. This is half monthly, this is monthly, this is couple months, and then this half year, this is yearly. Yeah. Notice that this amplitude are not constant. Frequency are not constant. Yeah. They are not the Fourier components. And the nice thing about this is that all the components are nearly orthogonal to each other. Yeah. Number 1 to number 2, number 2 to number 3, the inner product add up to nowhere more than 4%. This is the last two components. The last two components look like this. Only couple waves. I challenge Fourier for couple waves. They can make it orthogonal. It's not possible. Fourier orthogonality is established on infinite length. Yeah. And here, for any finite length, we have orthogonality. Yeah. Not only that, the sum of all off-diagonal components is only 4%. This is amazing to me because I did not impose orthogonality. Orthogonality is not a requirement, but it come out to be that. We'll explain to you why this is the case. Okay, later. And we can also reconstruct the signal from the decomposition. This is the last component. This add one more, keep adding. As you're adding more, it's getting more and more closer and closer to the data. And finally, when you add the annual cycle, it actually goes through each cluster of annual. And if I blow it up, you can see it goes through each annual cluster. But what I missed is the annual cycle has bimodal distribution. I only have mono model. Yeah, and that's where I missed. Fine, I will add half monthly, semi-annual. Once I add semi-annual, it will go through this cluster. But of course, I miss that. When you add monthly, half monthly, and all, you will add up, right? And when you add up all 12 components, and you compare with the original data, you get this kind of answer. That means the answer has no information. It means you add up to the original. What's the difference? The difference is 0 to 6, minus 6, 10 to the minus 6 power. Why 10 to the minus 6? Because the data I got has 6 decimals. Yeah, this is round off signal, round off in the computation. So I can completely recover the information, the data. This is not surprising because the expansions algebraically indicate that the sum of all equals to the signal. Originally, remember when I do Hilbert transformation, get that? Now, after the decomposition, if I plot the annual cycle, I will get this Hilbert transformation. That means out of this jumble of random number, I can pull out the annual cycle to be so regularly organized. Yeah, and annual cycle looks like this. They are amplitude high, amplitude low, different amplitude. Why different amplitude? Fortunately, the oceanographers and the geophysicists have studied this problem. The problem is that if I plot the envelope, you can see peak and trough, peak and trough. Turns out each peak is a El Nino year. El Nino year means the equatorial water is temperature get very high. When the equatorial water temperature is high, it gives more energy to the atmosphere. And atmosphere has more energy, so atmosphere moves more violently, and it's almost like a skier. When the skier spins, and the hand is holding or the hand is waving, it will change the rotating speed. Each time, the El Nino year is the peak. That means the atmosphere moves more violently, or the skier is waving the arm. So our length of day will be about 0.2 millisecond longer than other years. Yeah. Not much, but the fact that using this very simple thing, we can extract this information. That's amazing. Yeah. If you convert this eventually to time, frequency, and energy, this is the Hilbert spectrum. Yeah. So we not only have the component, we can have a time axis, frequency, we can compute from the time derivative of the phase, and energy from the amplitude. We can plot it out in this form, and this is what we call the Hilbert spectrum. So this whole course is going to talk about this sort of thing. This is the half monthly time, and half monthly time is fluctuating. Yeah, the frequency is fluctuating. That means half monthly time is nonlinear. It's not a linear thing. This has to be a little bit get used to, because the traditional people doing time, they have lots more components. How many components to get depends on how patient you are. Let me show you the way that the time cycle is determined before computer comes around. Before computers come around, they can predict time for years. Yeah, this is called the tidal machine. Yeah, the tidal machine. This is made in Germany. The German has a very good engineering skill. This has about 200 little gears like this. Yeah, it's on this layer, on the back layer, front layer, and the vertical. So they are all coupled. Yeah, each one gives you an astronomical tide term. There's the sun, the moon, the this and that, all together, give you that. This is a linear representation, because each one rotates at constant speed. Each one gives you a Fourier component. You add it together, give you the total time. Yeah, the guy has to be very ingenious to come up with this interacting linear components. It's this machine. Yeah. The adaptive base that we developed is complete convergent orthogonal uniqueness, but all proved a posteriori. Before I analyze it, I don't know what the base it will be. You have to give me data. I go through the procedures. Yeah. And after I go through the procedure, I can prove this completeness is given, convergence. Yeah, if I get a component, it has to converge. Orthogonal, we can check. Unique, we can check. So this is very, very different from the traditional view. The most critical difference from the traditional view is the nonlinear term. When we do a cosine omega t plus epsilon sine 2 omega t, if we perturbate the frequency, what happened? Instead of a cosine wave, it becomes sharp crescent and sharp trough. It's no longer like a sine wave, just because of the little phase perturbation. And when you do this little phase perturbation, you can expand it out as cosine omega cosine this minus sine omega sine that. And this term can be further expanded out with Taylor series. The leading term is 1. This leading term is the argument. Yeah. And you reconstruct that, recompute this as cosine omega cosine 3 omega. So you expand out as cosine omega 3 omega 5 omega 7 omega and so on and so forth. This is a Fourier series. Yeah, this is a Fourier series. This Fourier series representation gives you all sine summation of sine. So that's the Fourier view. Now, if you ask Hilbert how they view it, Hilbert said, well, take the differentiation of this. The frequency keep changing, oscillating. That's their view. So we have two total different views of frequency. Depends upon whether you want a constant frequency or time varied frequency. Now, the representation of this is that here is the fundamental, here is the harmonics. Yeah, the harmonics here, fundamental here. Yeah. And you can have more harmonics as you go on, if you have more time. However, if you ask Hilbert, Hilbert says no. Frequency is just a constant, but it's fluctuating. Both of these are mathematically correct. But which one gives you more physical meaning? I submitted that this has more physical meaning. In fact, you look at the original model, it's a phase fluctuating. What's a phase fluctuating means? It's frequency changing. Yeah. So this and the colorful wavelet kind of representation, both give you the nonlinear effect. But this expressed in terms of intra-wave frequency modulation. And Fourier, the Fourier type, including wavelet, give you in terms of harmonics. Harmonic distortion is nonlinear. Yeah. So why didn't we use harmonic distortion? Because it's not practical. Harmonic distortion represent nonlinear, always higher frequency components. But we all know, in reality, in the high frequency domain, there's lots of noise. So your signal will be swamped by high frequency noise rather than clean. Here, we have our signal all near the peak, all near the main frequency band. It's just the broadening of the frequency that gives you broadening of the frequency spectrum. That gives you the indication of nonlinearity. Yeah, we'll come back to this later and give you very detailed quantification of nonlinearity. Okay. When we look at this example, when I put epsilon equal to -1 and see what we got. We get a sharp crest and sharp trough. It's just like what we got the model. This is indicating that this wave has been strongly distorted. Yeah, this is strongly distorted wave. It's so much so that the amplitude is not constant anymore. So we cannot apply Hilbert transformation right away. We have to do first decompose. What do we decompose of? Constant amplitude, constant amplitude. What is this? This is a cosine function. Cosine function is the forcing function. So out of this signal, we got the cosine forcing function. We get the systematic point oscillation, system oscillation. This is 1, 0, 1, almost 2. This is 0.05. In a way, when we look at the physiological data, this is like a pulse, this is like your breath. Slightly modulate the pulse in amplitude and frequency. Yeah. So, and then we have a subharmonics. So out of this, we get 3 components. Yeah. If you actually carry out, you get more components, but the other components are transient, not very useful. When you convert back to the spectrum, this is the forcing function, constant Fourier, constant frequency. This is the system oscillation. Sometimes frequency is higher, sometimes frequency is lower. It will never repeat itself because by using epsilon equal to 1, we already get into chaotic. Yeah. How do we know this fluctuation up and down makes sense? We come back to the original data. This is the frequency. These waves correspond to that. It's a higher frequency. These waves correspond to this. It's a lower frequency. You compare these 2 waves. What you see is that this wave is a little bit wider than that wave. Slightly. Yeah. So, with this slight change, very minute change of the wave, this method, instantaneous frequency, immediately spotted. Is all right, I don't want the instantaneous frequency. I want to use Fourier based, like wavelet. This is fundamental, this is harmonics. Which wave is faster? You don't know. You will never know from this. And compared to this, it's very clear because it's quantitative, every point, no smear in time, nor frequency. Yeah. So this, yeah. The next one is, we can skip the next next example is global warming. We'll come back to that later. So what this means, it means instantaneous frequency is really, really important. Yeah. It offers a total different point of view for nonlinear data. Yeah. If we use instantaneous frequency, what we do not need is the harmonics. I submit the harmonics is actually a mathematical artifact. Why I say this artifact? Because I get one set of harmonics if I use Fourier. I get another set of harmonics if I use wavelet. And depends upon which wavelet you use, you'll get a different kind of harmonics. So the harmonics depends upon the tool you use, not depends upon the phenomenon. So it moves with the mathematical model you use. So it's a mathematical artifact. Now, if you use the nonlinear instantaneous frequency, I just only get one way that how the harmonics fluctuate. Period. Done. Okay. That's why I think the Hilbert spectrum instantaneous frequency is more physical rather than the artificial mathematical artifact of harmonics. Also, once you use that, because we don't integrate anymore, when you do integration, within the duration of integration, the time is smeared. So you cannot have the time precisely defined within the duration. But if you have too short a time, your frequency is no good. So the trade-off between time resolution and frequency resolution, you get this uncertainty principle. But in our case, we don't have that, because what's the time limit? I took a differentiation. I get 2 points, 2 neighboring points. I define frequency. Yeah. How large is the frequency? Depends on how large is the differentiation. So it's absolutely breakaway from the uncertainty principle. I have to declare, I'm not saying uncertainty principle in physics is wrong. Okay, that has physical implications. It's very different from what I say. What I'm saying here is that in data analysis, there's no uncertainty principle, unless you use the wrong tool. That means the integral transformation. Then you invite, you bring in with you the integral transformation, the uncertainty principle consequences. The adaptive base is important in non-stationary. Of course, one wave to another is different, but more important is nonlinear, because not only from one wave to another wave the frequency is changing. Within one wave, the intra-wave frequency. Non-stationarity most imply interwave. This is intra-wave. Within one oscillation, the frequency is different. Yeah. This is the beauty of the method. We give you exact value of, of that. So HHT established a totally different paradigm of data analysis. To summarize, basis Fourier is a priori. Before I see your data, you know what base I will use, sine, cosine. Okay? Wavelet, a priori. What wavelet you use, you have to tell me. You use Debussy, you use Kaufman, you use Haar, you use whatever. Yeah. There are very, very different numbers of wavelet. Myers wavelet and all kinds of wavelet. Yeah. The so-called adaptive wavelet is that you have a telephone book of directory. You flip over, so this wave looks like my wave. Okay, you use that. But once you choose that, say, but what if my path is changed from linear to nonlinear and back linear again? Then you will feed one part but not the other part. Okay, so in that case, it's still a priori determined. Hilbert is totally adaptive. Before you give me data, you say, what's the base you use? So I don't know. Give me data first. Yeah. And you change one point, my base changed. I don't have a preset mind. I have to look at the data. Because of this, the frequency definition is very different. Fourier uses integral transformation, sine, cosine. Wavelet use regional transformation. Yeah? The wavelet, long, dilation, and small. And all these are integrals. Here is differentiation. I take a derivative to get in frequency. And that get my time location so local. And that's why it's more powerful. Many people say that wavelet is a magnifying glass for data. Not quite. Yeah. This not only give you a global view, narrow view, but it can look down into the region that the wavelet fails, because wavelet cannot see intra-wave frequency modulation. And the presentation is energy time frequency. It can do nonlinear, yes. Non-stationary, yes. Yeah. Uncertainty, no. And harmonics, no. So this is the advantage that I will present in this semester in the course. So adaptive, I think it's the only scientific meaningful way to analyze data. is the only way to find out the physical process, not mathematics. Yeah. It's very physical, direct, and very simple. Yeah. The rest of this, the handout, talk about some history, some philosophy. You can read it for your own amusement. That's my view of all on the general science development. One of my teachers in college says the best the scientists can give to the world is result, not philosophy. So I will skip the philosophy part. You just go read it yourself, okay? And if you agree with me, fine. If you disagree with me, you can talk with me and we can discuss. I will not use the time in this class to talk about it. But nevertheless, I do want to tell you that the development of HHT has a very, very short history. It's only less than 15 years because the first time I thought of the idea was in 1995. And the first time I written it up in 1996. But the paper gets so long, it takes 2 years to publish. It actually gets accepted right away, but the Royal Society can only print 25 pages. My paper is 93. So it took 2 years for them to come back to me and say, replot this, replot that, and then squeeze all the figures and everything. So finally it published in 1998. Yeah. So it's a very short time development, but the progress is phenomenal. Yeah. Now it's getting used in all kinds of fields. Yeah. And we even have our own journal called Advancing Applied in Adaptive Data Analysis. It's co-edited by me and Professor Tom Ho from Caltech. So you can look at those journals which represent the frontier of research in that. But for those people in the RCADA, the research center, you are in present at the creation. The new method come out every month or every week or whatever. Yeah. So I think it's a very exciting place to be, and this method is a very exciting method for you to learn. For those that have better thing to spend their time, after this introduction, you don't have to come anymore. You can go back and do your own thing. But for those who want to learn the detail, nitty-gritty, this HH looks wonderfully simple, but the devil is in the details. Yeah. The detail has lots of nitty-gritties that is not totally resolved. That's what we're still working on. Yeah. So the rest of the semester, we'll talk about the details, not the general picture. This 2 hours introduction gives you the general picture. I think once I was in the class by Professor Xu Xianxiu. Xu Xianxiu is the father of Xu Xiaseng. Xu Xiaseng was the president of Tsinghua University, right? Xu Xianxiu is his father. When I was an undergraduate, Xu Xianxiu comes back to Taida to teach a course called Advanced Applied Math or whatever. So I went. Because Xu Xianxiu is such an important person, he missed all kinds of class. He will come in one day, and then the next week has no class. So at the end of the semester, the whole book was covered only first chapter, I think, something like that. It's very, very little. Then at the last class, he shared with us a secret. He said, smart people only read the first couple pages of the book. The rest of that he will figure out himself. So for this class, the introduction is the whole thing. And if you will come back, you get all details. You will not get a big picture anymore. Okay? Thank you very much. Yeah. Any question from my friends, my colleague in Tokyo? Okay, so if you have better things to do after this introduction, you can do your better things. From next time on, we'll talk about details. Yeah. All right. If you don't have any question, bye-bye. Till next week. Bye-bye. All right, 你们有没有 question? Now we can relax and can talk about Chinese. 有没有问题？你们要问问题啊！你们不要问问题，问问题才会 learn。OK。
就是 Hilbert 这个东西，我没有，就是他是创造了另一个新的那个概念学。
No. If you look at Hilbert's paper, you will never find Hilbert transformation among his paper. He never written anything. What he did, 他真正他做了，他从来没有写过一个 paper 叫 Hilbert transformation， 是他在做 Fourier transformation 的时候 find out Fourier transformation 是个 conjugate， 他这个 conjugate 也是个 transformation。那么然后后来的人因为是他第一个在一个 footnote 里面讲的，所以就叫这个叫 Hilbert transformation。
但他也是造了一个 conjugate 的，就是说，比如说我们，就是我了解说，我有一个 cosine， 然后我创造一个 sin，
对，
所以这个，所以还是创造了一个这个东西。
对。
那这个东西这样创造是对讯号来说，这样子做是不是？
这样做是 wonderful 啊，但是这个有一个很大的 catch， 就是说，你假如把一个 sin 它是出来 cosine， 你把 cosine 出来 sin， 那你把一个 general 的 function 它出来不是，所以这个 Hilbert transformation 啊，它本身是 equivalent to Fourier transformation， 它本身是 linear， 所以它对 nonlinear 的东西它没有办法，所以我们现在已经不用 Hilbert transformation， 因为 Hilbert transformation 对 nonlinear signal 它不会给你 exact solution。它有好多 limitation， 它的 Hilbert 的 limitation 跟 Fourier 一样，
它都是线性的那个。
对，线性的。你讲不是线性，他们没办法做。但是我一开始的思路是根据 Hilbert 这样来的，所以我要找什么样的方式适合于 Hilbert， 所以这样做出来的 EMD， 结果呢？到了这个数学界，这数学界一看 Hilbert 眼睛亮了，因为 Hilbert 是大师，所以大家都去找 necessary and sufficient condition for signal satisfy Hilbert transformation。这个不是我们要的，因为我们的 signal 是 all kind。你说你找出来这个 class function 那个 class function satisfy Hilbert， 或是 that has anything to do with me nothing， 因为我的 signal 不可能是这个 class， 也不可能是那个，是来的是随意的。所以我们一定要找出来一个方法，能够撇掉它这个 Hilbert 的 limitation， 撇掉它 Hilbert limitation 呢，我们就找出来了那个方法，就是说根本就直接去做 arc cosine， 或者直接做 quadrature， 那都是等于是直接去找 arc cosine。你写出来方程是 a time cosine theta， 我把 a normalize 以后就是 cosine theta，arc cosine theta 就是我的 answer， 那个比 Hilbert transformation 直接多了。OK， 你算 arc cosine 的时候是不定的，里面还有一个多的，但是我不要 arc cosine， 我要 derivative， take derivative 前面 constant 不见了。
这还有一个 take derivative 的时候是，这里刚刚提到一个什么 stationary phase approximation，
啊，
这是一个 global 的 approximation， 还是说它是 local 的 approximation？
它那个等于是 local 啊。它相当 local， 因为它要 contribution， 那个 stationary phase 就是说我有这么一个 integral， 哪一点对我的 integration contribution 最大？那 contribution 最大的地方就是 phase stationary。我们回到那个里去啊，我跟你讲为什么是 stationary phase 是很要紧，是很合理的一个猜想啊。 啊，不是时间到了不要讲，你们可以走，问问题的可以待下来。哎，我刚才我点的是那个，怎么不见了？哎，越走越后。这个，我刚才是这个。你知道这个 Fourier transformation theory 有一个啊，就是我任何一个 function， 去乘了这个 Fourier 啊，我这个 integration 都是零，都会是零，因为它那个 fluctuation 越高，就是等到这个 frequency 一高的话，所以这个 function 对它的 transformation 啊，这个 function 它是 fluctuate 很快的。什么时候它的 fluctuate 它对这个 contribution 最大的，就是这个 phase 是 phase 变得最小的时候。你 phase 变得越大 frequency 越高，就 cancel out 呀、这个变得最小积分，
只要有周期的话，
对，就 cancel out。
它最低的时候，
不是最，它变化最小的是 constant 时候，这 constant 时候叫 stationary phase。
它其实是西塔等于欧米伽 t， 然后再给它，那这个是西塔除以 t 是平均。
那不，西塔跟 t 的微分是零，在那一刹那它是平稳的，比较平稳的。
哦。
它变化小，因为你变化一大就是零了。这个叫好像叫 Lebesgue integral， 不是Lebesgue，那个叫叫什么 theory？ 我们回去可以找那个 theory。OK， 你们没有问题，我们就这堂课就下课。以后我们可以这样，他们走了以后，我们假如要讨论的话，我们可以用中文再讨论一下。
到11点都没关系。
哦，到11点都没关系。啊，是还是有人买的，他11点有人用是吧？
目前是就借2个小时。
哦，其实我想他这个地方不会有人。OK， 谢谢。